Good morning, everyone. Am I audible?
Yes, yes.
First of all, let me thank to our top leadership that includes Honorable Chancellor and Founder Professor Syed Wasim Akhtar Sahab, Pro Chancellor Dr. Syed Nadeem Akhtar Sahab, Vice Chancellor Professor Javed Musabbat Sahab, Director HRDC Professor Syed Akil Ahmed, and Dean Faculty of Science Professor Abdul Rahman Khan to allow us to organize the faculty development program on current trends in theoretical and experimental research in physics under the aegis of Human Resource Development Center, Integral University. Today is the third activity of the lecture series of Faculty Development Program. It is my honor to introduce the distinguished speaker and resource person, Professor Sushant G. Ghosh, Professor and Director, Center for Theoretical Physics, Jamia Millia Islamia, New Delhi. He is also visiting associate of IUCAA Pune. Professor Sushant Ghosh has over 25 years of experience in academic and research and guided 16 PhD students. He was first director of research and founder director at Multidisciplinary Center for Advanced Research and Studies, Jamia Millia Islamia. Formerly, he had several positions such as Associate Professor in the Department of Mathematics at BITS Pilani, Dubai, Honorary Professor at School of Mathematical Sciences in University of KwaZulu-Natal, South Africa, Fulbright Fellow in 2018 and visited 16 universities in the United States of America. In 2015, Professor Ghosh with his colleagues obtained Visitors Award given by President of India, Shri Pranab Mukherjee. There is a huge list of honors and awards given to Professor Ghosh. Here, let me mention few awards. Fulbright Fellow 2018, featured in the Stanford list of top 2% scientists, MHRD LEAP program 2019 at Jamia Millia Islamia and University of Virginia, member of Indian Delegation First Forum of BRICS Network, University, Russia, member of ITUN project, India, Thailand and Uzbekistan Network Project funded by ICTP Italy, Classical and Quantum Gravity Reviewer Awards 2018. There is a huge list of research grants and fellowships given to Professor Ghosh. For example, Gyan Course, SERB DST projects, Indo-South Africa project, ITUN funded by ICTP Italy, research grants from University Grants Commission, Teachers Fellowship, Faculty Improvement Program, UGC New Delhi. He has also good administrative experience that includes founder head Science College Nagpur, NAC coordinator of the college which got 5-star rating, NAC core committee member for JMI, nodal officer Vishwesharya PhD program for JMI, coordinator relating BITS Pilani, Dubai. Professor Ghosh visited several countries such as United States of America, Russia, South Africa, Uzbekistan, Thailand, and Dubai. He is member of professional bodies that includes life member Indian National Science Congress, Calcutta, life member Indian Mathematical Society, New Delhi, life member of Indian Association of General Relativity and Gravitation, Pune, life member of South African Gravitational Society, South Africa. He has more than 172 research papers with total citation 8,500 and H index 55. Let me invite Professor Sushant Ghosh to deliver the FDP lecture.
Okay, am I audible?
Yes, sir.
Okay. Thank you, Salam, for your kind words. First of all, I'm grateful to the university for inviting and giving me chance to speak. Can I? You are audible? Audible?
Yes, sir. Yes, sir.
Okay. So, giving me chance to speak on this FDP program. Thanks to the administration of Integral University, I'm very really honored to be here. Especially thanks to our student Shalam, who has done PhD with us, and he was a great researcher at CTP and one of my favorite students at CTP. Right. So, with this introduction, let me start. So, topic is seeing the invisible, strong gravitational lensing by rotating black hole. Invisible means which we cannot see, which we cannot see. For example, I am wearing this lens. Why? Because I can't see. When I put the lens, I can read. Similarly, if there is a distance lens, I can't see the distance, but with this lens, I can see. So, in the similar logic, you have a gravitational lensing. Gravitational lensing. So, let's see. So, next slide came, Shala. Yeah. Okay. So this is left side is optical lensing, right side is the gravitational lensing. In the optical lensing, light bends due to refraction at the spherical and focuses into the eyes. Gravitational light bends around a concentration of mass such as galaxy, star, black hole and refocuses somewhere else. Right? So we will be talking about the black hole as a lens. Lens can be galaxy, can be star, can be any massive mass. Right? So I will be talking about the black hole. Right? So let us see what is gravitational. A process where light is bent due to gravity of the body. Right? This massive body can be galaxy, cluster, black hole, which serve as a gravitational lens. Right? And it results into multiple images of the source. Single source may create multiple image. Right? So this is also called cosmic telescope, where light bending around black hole let us help to probe deep gravity regimes or strong gravity regime, and it is a tool to testing general theory of relativity and modified theories of gravity. So again, similar slide, but I want to be very careful, right? So there is a distance galaxy here, and Earth is observer at the Earth. So you can see the galaxy is black is blocking the distant galaxy. So light came from the photon come from the source, because source is a bright object, and it bends around the galaxy or the black hole and reaches Earth. So it creates two virtual images. You can see same source galaxy is created two virtual images. So that is the lensing in the in this diagram. So gravitational lensing is a visual effect caused by the distortion of the space-time caused by the large mass, can be galaxy, can be black hole. The path that light follows no longer remains straight, because you can see the bending of light, which you must have studied in the early classes, right? And this is observed. This is observation. Right, this is exactly observation. Hubble measures the deflection of straight by foreground object. So this is the real position and the observed position. And there is a mass concentration of mass which is white dwarf. This was really observed in the gravitational lensing, but not by the black hole. But we'll be talking about the black hole. So origin of the gravitational lensing. First predicted by Albert Einstein in 1905 when he was working on his theory of general relativity. That was the first time Albert Einstein projected. Although it was also showed in Newtonian gravity, but I won't talk about that. Einstein prediction were confirmed by the Sir Arthur Eddington in 1919 through his observation of the solar eclipse in the principal, that is in the Africa, right? what affects. Now right side is the observed thing, right? Observed thing. Einstein cross. You can see that same object creating four objects in the form of cross. So a galaxy situated between Earth and quasars, 8 billion light years away, creates a gravitational lens that bends the quasar light, creating four bright outer objects in this image. The original image creates four objects. This second is very important, which was recently observed by the James Webb telescope. Everybody knows that James Webb telescope. An Einstein ring, very, very stunning. An Einstein ring recently captured by the James Webb telescope. Right? So that is second. So this is. And same thing I'm putting in the more proper slide. The left side top is again a ring observed, and this is Einstein cross, and then there are multiple images. So single image can create infinite image in form of Einstein ring, four image in terms of cross, or it can create two images. So that is all possible, right? Next, history. What is the history? History that, as I said, Michel was a geologist who proposes the black hole concept in the 1970, 1784. Einstein GR predicts both light bending and black hole because we are talking about black hole. Eddington confirmed light bending first GR test. In 64, Wheeler, very famous scientist Wheeler, coined the term black hole. 79 first lens quasar found black hole powered, right? And recently, this two right image, very important. Everybody must have seen this image. That EST Observer 2019 released the image of two important black holes. One in our own galaxy, which is Sagittarius star up top, and down is what M87 in the nearby Virgo cluster, right? So these two are the very important aspect of the lensing, creating image of black hole, black hole, right? Now let me give the schematic diagram. This is the schematic diagram. I already have given you the detailed diagram. This is the schematic diagram, right? So here there is a source A, as in the red, and the light emit from the source and bending because of the lens L is the lens L, that is black hole, and it reaches the observer. This diagram is very important for us. It gives everything about the lensing, right? So so the yellow line is the path of the photon, which is bent because of the black hole, right? So observer will see the original image at here, right? The source is here, the observed image is this here. It is shown in the gray. So that is the observed image. Now photon can travel anywhere, so it can create image anywhere. I have just shown one image, but it in principle, as I said before, can create multiple images. Right now, x0. So first of all, you see x0. X0 is the closest approach distance to the path of the photon. That means where the photon bend the direction of, right. Now u is the perpendicular to the initial the final direction of the photon, and u is the also perpendicular to initial. So so deficient, this is delta phi is the total angle change, right? Now alpha d is called deflection angle, which is what we are interested in, and alpha d is nothing but delta phi minus pi. You can see this is pi, very simple, delta phi minus pi, right? Now theta is the angular position of the image, right? S is the beta is the angular position of source. So this diagram here is very important. So you have your source, you have lens, and you have observer. Distance between source and lens is DOL. Distance between similarly lens and source is LS, and OS is observer and source. Right now, this is the diagram which is very useful totally. So first of all, we are interested in deflection angle. That means how much the ray is bent. bend, deflection angle. That is very important. We have to understand. So we need a black hole. You see, you need a lens. Lens is black hole. So we need a black hole. So I want to talk about black hole first. Then I will come to the lensing. Right. So before that, I just want to say one more. Next, okay. See, now the red is the path of the photon. Both of it is bending. Again, it is bending. And in the second diagram, the red ray is making a orbit around black hole or lens before reaching the observer. In principle, the ray can make any number of orbits around the black hole, around the black hole. So right. So left side is called lensing, weak lensing. Only slight deflection and reaches the observer, create an image. So this is the image created. In the right hand side, before reaching observer, it makes a several loops. It can make one loop, it can make two loops, it can make three loops, it can make n loops. So it will, in principle, create every loop will create another image, right? So you, in principle, single source can create n images, infinite images, right? So this is weak lensing. Now, what is black hole? First of all, I just want to give one minute to what is black hole. What is black hole? If anybody asks black hole, then this is the black hole. You can't see anything. The can't see anything, and black hole doesn't emit anything. So if you want to look at the black hole, it is dark, right? But this is slightly time delay. Oh, next. Okay. So I can see that this is a black hole with accreting matter. Accreting matter. So right, the matter which is accreted, it can emit. So that is the light. Right. This is the light. So in the center, you can see there is a dark region, that is black hole, surrounded by the matter, surrounded by the accreting matter. So that can emit, and it shows the silhouettes. So this is a black hole with accreting matter, and this is a simulated image of the black hole. Okay. Now, if I want to give exact definition, if I want to give exact definition, black holes are region of the space where gravity is so strong that nothing, even light, can penetrate. Right? First predicted by Einstein general relativity in 1916. Einstein predicted the GR in 1915, and Carl Schwarzschild, a German scientist, gave the first solution of black hole, which is called Schwarzschild black hole. Very, very important. The black hole is corrected by two quantities. One is event horizon, another is singularity. Right? The event horizon is point of no return. So black holes in general relativity are the solutions of vacuum field equation. थोड़ा delay, time delay. Okay. So it is solution of vacuum field equation of Einstein general relativity. So when G mu nu is equal to 0, right hand side is 0, no matter, then you get a black hole solution. Very famous four black hole solution. The third is very important. First is static neutral, second static electrically charged, which is Reisner-Nordström, and third is the Kerr, which is very important, a rotating neutral black hole. Why I'm saying rotating black is very important? Because astrophysically, all black holes are supposed to be neutral, and they are rotating. So the fourth is very important, which was discovered after almost 60 years of 40 years of the first solution. Right? It was discovered in 1964. And there is a conjecture which is called no hair conjecture, which was given by Wheeler. which says that stationary isolated black hole in GR are uniquely characterized by the three parameter mass, angular momentum, and charge. All other parameter, if it comes, because they can come from the modified theories of gravity, are called here, right? So it means that stationary isolated black hole in GR are therefore described by the Kerr-Newman black hole. But what about the astrophysical black hole? Astrophysical black hole are supposed to be neutral. Normally, what I say, this is the three parameter. Black hole can eat everything, but it is described by only three parameter: mass, angular momentum, and charge. But what about astrophysical black hole? The black hole is supposed to be astrophysical black hole is supposed to be neutral, and therefore Q is negligible. Q is negligible, and therefore astro black hole are described by the Kerr black hole. Kerr solution. Kerr solution. Right. This is the famous Kerr person who gave solution of the Kerr solution in 1960s in half page paper of the PRL, famous PRL paper. So this is Kerr black hole. Very. I just want to glance through what is Kerr black hole. Mathematics, little mathematics. Don't worry if you cannot understand mathematics, but it is very simple mathematics. So this is a line element of the Kerr black hole, which generalize the famous Schwarzschild solution. Right now, this is a distance space-time interval. You can see there is a problem at sigma is equal to 0 and also delta is equal to 0. There are two problems: sigma is equal to 0 and also delta is equal to 0. Now sigma is equal to 0 correspond to a curvature singularity which is physical singularity, which is a curvature singularity, and where your sigma r square plus a square cos theta is 0. That means you have a ring singularity, because r square a square cos square theta will be equal to 0 when r is 0, theta is pi by 2. So you will get ring singularity. The other singularity is delta is equal to 0, which is a coordinate singularity, and it corresponds to horizon of the black hole. As I said in the beginning, the black hole is governed by two quantity. One is singularity and is the horizon. So these are the two horizon. This is famous Kerr black hole, and it has important surface which is shown in this diagram, right? So it has a horizon, then it has a static limit surface, and it has a what singularity which is at the center. On the right side you can see it is a ring singularity. The region between the white portion is the black hole, and boundary is horizon, and there is a static limit surface which merges at the pole, right? The static limit surface and the event horizon merges at the pole. You can see that pole. The blue region is very important, where the particle can stay and it has to rotate around the direction of the black hole, and it is very useful to extract energy from the black hole. So this is Kerr black hole, but we want to generalize the Kerr black hole. Kerr black hole, right? I want to generalize the Kerr black hole. So this is called non-Kerr black hole. The difference between the previous solution and this solution is now m is a function of m of r. So I am taking one of this solution. So m is m of r. Rest of the property is exactly same. And this black hole reduces to Kerr black hole when m of r is what? Capital M. So this black hole reduces to capital M. When uh, when when it is capital M, then you have Kerr black hole. So I will use this metric. Mathematically, if you don't understand, no problem, because I will be telling you story around this, so it will be very easy to understand. But this is a black hole. Now this is a generalized non-Kerr black hole. Any Kerr black hole different from Kerr black hole is called non-Kerr black hole. So this is the non-Kerr black hole. Now MR I can take anything. So if I take MR is equal to M, then it is Kerr. MR is equal to M minus Q square, it is Kerr-Newman. And then second one is black hole which I am taking, which is Simpson-Wheeler black hole, and it is also lead to a ghost black hole which was given by me, right? So it is the problem which was in the previous slide. There are many black holes. It contains many black holes. I will be talking about second one, Simpson-Wheeler black hole, which is very important. Black, right? So metric is exactly same. Exactly same. Instead of m of m, you have m of r. There is an additional one term under root of r square plus l square. So if l is equal to 0, it becomes what? Exactly, exactly Kerr black hole. So this is a rotating Simpson-Wheeler black hole, and it is also has singularity. It has also horizon, which I will not discuss because my main aim is to discuss the lensing, and also it has a mirror symmetry. That means if I take r2 minus r, it is exactly same. So it is composed of identical portion around r is equal to 0, exactly enter, right? So this can be either black hole or traversal wormhole, depending on the parameter L. And why it is called rotating Simpson vision? Because when A is equal to 0, it becomes a very simple spherical black hole, and L is equal to 0 further will make it Schwarzschild black hole. So this is very simple extension of the Kerr black hole, right? So I want to do lensing. I want to first find out what is the deflection angle. Deflection angle for this metric. As I said, deflection angle are already shown in the diagram. Already shown on the diagram. But what we do before proceeding for the calculating deflection angle, we want to know that for which parameter this solution will represent black hole. It doesn't represent solution for all the parameters, right? Just remember, very simple. So I just want to know for which parameter it is a black hole. So this is the parameter space. You can see slide. Okay, now you can see rbh1, rbh2. We want to work only for the parameter where it is a black hole. So rbh1 is the black hole where there is one horizon. RBH2 is the black hole which is has two horizon, right? So here I have given condition in the next line, condition for two horizon. L has to be less than 1 minus under root of 1 minus. So I will concentrate only on this region where there are two horizon, RBH2. That means L can be from 0 to 1, but A can be from 0 to 1, but L is restricted. L is restricted, and it can be also at the most equal to 1. So this green region I will be taking, that is called the parameter space. So let us find out. So more simple thing in simplified diagram. So I want to investigate RBH2 where the black hole has two horizon. Okay, coming back to the picture of deflection angle. So same picture which I showed earlier. What is happening? What is happening? I want to calculate alpha d. So what we are doing? Understand? Don't worry about mathematics, right? We are taking the motion of the photon, right? Photon motion. So we will consider equation of motion, photon motion, right? So that we will consider, and we will consider strong lensing. So I am considering motion of the photon. So I have to consider with the Hamilton-Jacobi equation. And we have few assumptions. The source and observer are considered far enough, because otherwise it will be affected by the gravitational field of the black hole. So they are very far, and we can say they are at the infinity. Also, we consider source to be almost aligned along the optical axis, little bit away from the optical axis. In the previous diagram which I showed, it is little bit away from the optical axis, right? And also we consider light propagation only in the equatorial plane. Theta is equal to pi by 2. This is a simplified assumption. Then the metric is written as this: ax dt square, bx dx square, cx d phi square minus 2x dx dt d phi. This is the metric, general metric. It can be this recipe is applicable to any metric. I have taken social particular example. but you can take any. So in general, AX BX. So this is simple form. This is simple form. Now I want to consider light propagation, so I have to consider Hamiltonian-Jacobi equation, right? So this is your okay. This is your metric. Then you can write Lagrangian. Lagrangian. You can see that the metric is independent of t and phi. That means if I take t to minus t, then metric doesn't changes. Also, if I take t and phi simultaneously to minus t minus phi, the metric doesn't changes. So it corresponds to two killing vector, and they correspond to two conserved quantity E and L. E and L. So simple mathematics, very simple mathematics, and then E is equal to given by E is given by what? Minus this is scaling vector. This is scaling vector. So E is given by this, L is given by this, and if you put the Lagrangian, then it will lead to two simultaneous equations. Very simple, two simultaneous equations. Right. So these two simultaneous equation you can solve to get t dot phi dot right, and then I can use the null condition. Null condition means metric is because we are using photon obeys the null equation. Then you can put this is equal to 0 and put the value of t dot phi dot. That will give us the radial equation. Theta is equal to pi by 2 gone. So we get now 3 equation. Instead of 4 equation, we get t equation, we get phi dot equation, and also equal we get r equation, which we have written in terms of x. Right. So these are 3 equation, and this need not to be solved. First order equation is enough for our calculation. Very simple calculation. Right. So these are 3 equation fully reduced to first order differential. So last equation, 12 equation, you will see. I'll rewrite. Right. This is the first term is kinetic energy term. Second is this. So we will call right. Second term is V effective. V effective, because it is not exactly potential term, but it is V effective. Okay. So we have rewritten the last equation, which is writing that is extra term x dot square as V effective. Right. As I showed in the diagram, at turning point, V effective will be equal to 0, and V effective derivative will be also equal to 0. Right. At the closest approach distance also, V effective will be equal to 0, because radial, you can see first equation, when you change the direction, the radial velocity will be equal to 0. Therefore, x dot is equal to 0. Therefore, V effective will be equal to 0. So when you solve V effective for L by E, because this equation is in terms of L and E, you can solve as a simple equation in terms of L by E. It will give me the value of impact parameter. L by E is called impact parameter. So every photon will have some angular momentum and energy. Now, as I said, before reaching the observer, the photon can make many loops before reaching the observer. Right? So that is called photon sphere or unstable photon orbit. So what is happening at that? Not only V effective is 0, V effective prime will be also 0, because it is making circular orbit. Right? The acceleration is also equal to 0, and that will give me the radius of the photon. That is very important to us. Right? So this is photon sphere and impact parameter. Two important. I'll bring another diagram to very liquidly. I will explain this with the very simple diagram. Simple diagram. Let diagram come. It's a bit slow. Yeah. Diagram. Okay, came. Okay. So you can see that right hand side is showing the motion of the photon from the source. Right. This is a source, light source coming towards the black hole. The dark is black hole, and left hand side is the effective potential. The plot of the effective potential. The black line is very important. Black line is very important. You can see in the diagram the V effective is 0, and it has a local maximum. So V dash effective is also equal to 0. V dash effective is also equal to 0. So this is correspond to unstable photon orbit. If your impact parameter is more, the black hole, this light rays will scattered away, and if the black hole, the impact parameter is less, then the photons will be absorbed. So three, the photons may be captured, may be scared, or form a bound orbit or unstable photon orbit. That is very important. The black is one is very important to us, right? That is what will help us to calculate the diagram. Okay, or I can calculate the impact parameter. That is not important for us. Now I will calculate the deflection angle. Again, come back to the picture. Coming back to the picture, I will show you the picture. Sorry, I will show you the picture again. Deflection angle. Already I have shown that V effective potential derivative will give us the radius of the photon sphere. And now I want to calculate the deflection angle. Deflection angle. Diagram. Diagram is not coming. Shalam, you are in.
Yes, sir, we can see the diagram.
No, say next diagram is not coming. Next diagram is not coming. 1 minute.
Okay.
Next diagram is not coming. This came. Okay. Can you see that red one, Shalam?
Yes, sir.
Okay. So I want to calculate alpha d. You can see I want to calculate alpha d, and in the diagram it is delta phi minus pi. Very simple calculation, delta phi minus pi. So I will calculate that deflection angle. You can see alpha d is twice x0 to infinity, because the source is very far and observer is also very far. So it will be x0 minus infinity to infinity. X0 is the closest approach distance where the photon bends, right? So you can write twice x0 to infinity delta phi minus pi. As I said, alpha d is delta phi minus pi. So integration, very simple. So delta phi upon d, delta phi you can write as d phi upon dx differential. Very simple. Now I will put the value of t dot and phi dot and x dot, which we have calculated earlier. Diagram. Okay, so I can substitute phi dot and x dot, and that will give the deflection angle. Very simple calculation. It has to be calculated. It is long calculation, but we don't have to worry. You have to understand that it will give us the solution for deflection angle. Okay. थोड़ा सा टाइम लैग है. Next diagram. Okay, I can calculate alpha d alpha d, that is deflection angle, and which is this. You can see that it is in terms of alpha d theta minus a log theta dol minus 1 upon um. Now um is impact parameter, and theta dol is also u. It is also u. So you can write it is equal to u upon um. So what will happen when u reaches um? That means when u reaches critical photon radius, m is the photon sphere radius. So when u reaches um or x0 reaches xm, this will have infinite. The deflection angle will become infinite. Deflection angle will become. So deflection angle is calculated, and very simple with the help of this diagram. And I have plotted the deflection angle, showing that when the closest approach reaches the impact parameter or the critical impact parameter of photon sphere radius, then it is showing divergence behavior. So this is the gravitational lensing. So we have mainly calculated the deflection angle. First of all, we have calculated deflection angle. Now what else? After deflection angle, we have to calculate some observable, right? Other observable associated with lensing. Right. So I move to the next slide where I have shown you in the diagram three angles: theta, beta, and alpha d. Theta is what? Theta is the image of the what? Theta and beta. Angular position of the source is beta. Angular position of the image is theta, and alpha d is deflection angle. And you can connect this triangle as you do in the optics, which is beta is equal to theta minus DOLS upon DOS delta alpha n. So this is called lens equation. It is exactly same as in the optics alpha n. Now what is delta alpha n? Is what? Extra offset angle, extra deflection angle, because the photon makes a loop, many loops before reaching the observer. So every loop will be having 2n pi angle. Every loop will be having 2n pi. So you can subtract those extra offset angle, and you get what? This. So this is called lens equation. Now we want to see when your beta is zero. See this equation when beta is zero. In this equation, you can see when beta is 0. Beta is 0 means what will happen? The source, observer, and lens exactly in the same line. They are in the same line, and then there will be a very nice effect, which is Einstein ring, which I shown you before. I want to show that when the source, lens, and observer are perfectly aligned, then you get Einstein ring. And this is what is the schematic diagram in the next diagram which I have shown. The Einstein ring, very important, where your source generates infinite image. Now, how you can see in the normal life, if you have suppose, and this is the ring, this is the Einstein ring which I plotted for the supermassive black hole, because I want to apply the lensing to the supermassive black hole. These are four black holes: Sagittarius in our own galaxy, M87 star in the nearby galaxy, and two other black holes. So let us say by different color. So Sagittarius A star, because it is closest to us, caused the biggest Einstein ring. Now, if you want to observe, see the more schematic picture, the next diagram will illustrate more schematically the Einstein diagram. So a special case of gravitational lensing in which the source lies exactly behind the lens, a ring like image will be produced called Einstein ring. Einstein ring. This is Einstein ring. Very important. Earlier also I have shown. Now I want to show you how you can see Einstein ring. Suppose you have a Einstein. Suppose you have a wine glass. Everybody must have seen a wine glass. I can show you a wine glass if you want. Right. This is a wine glass. Now it has all properties of black hole. If I put a lamp here, and see here, it will see like an Einstein ring. Salam, okay. You can see it is an Einstein ring. So you can see in general, it can, if you tilt it, it will give two images. If you tilt further, it will give four images. So this is the preliminary picture of the gravitational lensing effect seen with a wine glass, and it is showing Einstein-like ring. Einstein-like ring. Now let us move to the observables. Observables. Right now, three observable, many very important three observable. You can say theta infinity as r magnitude. As I said, there are infinite number of images can be formed. The first image will be formed, second image will be formed, third image will be formed, and there are infinite images of be formed. So theta is the angular position of the innermost image. Innermost image, right? So you have is the angular position of the, sorry, theta 1 is the angular position of the outermost image, and theta infinity is the angular position of the rest image, because the distance between rest image will be almost negligible, and r magnitude is the ratio of the flux of the first image and the other images. R magnitude. Now what is the meaning of r magnitude? If R magnitude is 100, then first image is 100 times brighter than the other images. That is the meaning. So you have theta infinity, you have separation between two images, and R magnitude. These are the three observable, which is very important for us, right? And that you can calculate using lens equation and this simple geometry, very simple geometry. Theta infinity is the angular position of the other images. Theta 1 is the angular position of the first image, and S is theta 1 minus theta 2, separation between two images. R magnitude is the flux ratio of the flux of the first image and the other images, right? So these are the three which we have calculated, right? This is the diagram which makes you things very simple. Okay, so this diagram I'm showing for a layman, that before reaching to observer, the photon makes several loops and creating the images. It is heavy image, so that's why it is taking time to come. Yeah, you can see that without making loop also it is reaching observer, making one loop, creating one image, first image, creating second loop, create second image, creating third loop, will create third image, and so on. You can see that separation between first and other loops are, you can detectable. All others are almost very order, low order, very small, right? And it is very difficult. I will show you, it is very difficult to find the separation, right? So this is the image. Now I have calculated, we can calculate separation. We can calculate for our rotating black hole, and we can see that it is it is more than the Kerr black hole. The separation is more than the Kerr black hole. Kerr black hole is in the black hole, because always whenever we do calculation, we calculate compare with the Kerr black hole. So green, as L increases, you can see that separation is also increasing in all the figures. Whether you increase A or you increase L, the separation increases. This is what I've shown in this diagram. And similarly, R magnitude decreases. R magnitude is decreasing. That means that Kerr makes more intense image or more brighter image compared to the Schwarzschild, rotating Simpson black hole. Right? Now, this has been applied to two important black holes, Sagittarius on the left side and M87 on the right side. Right. So this is the summary of the two black hole. The only thing is that when we take Sagittarius or M87, the Kerr black hole, if it is taken as Sagittarius or M87, the Kerr black hole form more intense image compared to the rotating Simpson black hole. Okay, time delay. In the figure I showed that before reaching observer, it makes one round. The first round, first image, second round, second image. So there will be time delay. The time delay is very important. So time delay between first and second image, when they are on the same side of the lens, can be approximated using delta 21 is equal to 2 pi UPS, and which is equal to 2 pi theta infinity dul. Anybody, if he is interested how I got this, I can explain later, because we have short of time. So this will be equal to this. And it depends on the distance. Obviously, the light coming from the more distant black hole will take time. So this is distance and also on the size of the black hole. For example, if you take Sagittarius star, it takes only 5 minutes, couple of minutes to make a photon to travel around the black hole. Whereas in M87, it is days, it in terms of days. So this can be calculated. This can be calculated for the various black hole. I have also calculated for all black hole, all black hole, Sagittarius A star as well as M87 and other black hole. Here I have shown only for Sagittarius A star, M87. So you can say that Sagittarius A star is only in the minutes, only in the minutes. Time delay is only in the minutes, and theta infinity, which is the angular position of the innermost image, is in micro arc second. I'll just tell you what is micro arc second. I know everybody knows, but for the student, I will tell you what is macro axis. But important thing is that time delay in the Sagittarius A star is in the minutes, whereas in M87 is in the hours, which I showed said earlier that it takes photon takes hours to travel around the M87 because it is very big. It is 10 to the power 9 solar mass, very big, right? So that's why this time is enough for any astronomical observation, any observation, and but it has other observables should be also satisfied. So we have applied formalism to two supermassive black hole, very important, Sagittarius and M87. So before that, I just want to flash one slide on the what is arc second. Arc second. So degree, you know that is a full circle, 360 degree. Arc minute is 1 by 60. Arc second is 1 by 60 of arc. So it is 1 by 3600 degree. And therefore micro arc second is 10 to the power minus 6. And 1 parsec is 3.26 light years away. 1 kilopark is 3.26 into 10 to the power 3 light years. The Shyam is expert for this, and but for benefit of student, I have put this. And 1 megaparsec is 10 to the power 6 light years away. Right. So these two black hole I'm talking about, the M87 and Sagittarius A star. We have applied entire formalism to this black hole, which was observed by recently by EST. M87 in 2019, observed in 17 but released in 2019. Sagittarius observed also in 17 but released in 2019. So you can see the mass is 10 to the power 9 M87, whereas Sagittarius is 10 to the power 6. But the distance is 8 kiloparsec only for Sagittarius, whereas distance for M87 is 16.8 megaparsec. So basically, the left hand side is very big, massive black hole, 10 to the power minus solar mass. But when we see from the Earth, both are looking very similar. This is the picture released by the Event Horizon Telescope, Mary must have seen. So what we have done, we have applied our formalism to supermassive black hole. So for M87, angular position is from 14.7 micro arc second to 19.8 micro arc second. Right? Theta infinity innermost image is 14.6 micro arc second, which is very small, 19.7. But the separation is in the nano arc second. Nano arc second. Time is in the hours. Time, you can see time is in the hours, 213 hours to 289 hours. But separation is in the nano arc second, which is very small. And we cannot resolve by the current astronomical facility which we have. The EST has 12 telescopes, but they can resolve around 20 micro arc second. So this cannot be resolved. So at the moment, what we can say that the Kerr black hole and supermassive Simpson-Fisher black hole are, are cannot be distinguished, undistinguishable from the current observation facility what we have. This we have published paper in the series of the paper. I have shown one, but we have published in the series of the paper. Right? And all this data which we have calculated is put in the I have put in in table, but nothing. I mean, it is very difficult to understand plot. Just showing that all lot of calculation has been done, and theta one, s, and r magnitude, everything is calculated for supermassive black hole. I have told you the gist of the data, but if somebody is interested, I can tell you detail. Right? So we have examined the effect of the parameter L on the deflection angle, lensing observable theta infinity as r magnitude in the strong field observation. Right? So it turns out that considering if we consider Simpson-Fisher solution as supermassive black hole, Sagittarius and M87, and other black hole, we can say that these two black hole, the Kerr black hole, if I consider as a supermassive black hole, and Simpson-Fisher as a supermassive black hole, the two black holes are not distinguishable by the current event observation we have. In future, Event Horizon Telescope is trying to add more telescope, and they will increase. And also, they are sending the telescope in the space telescope, then we may be able to have better accuracy. At the moment, we have observed only two black hole, M87 and Sagittarius A star, but in future, it is possibility that we can observe more black hole, and in future they are trying to take the picture of the, at the moment they have taken picture of the black hole. In the future they are trying to make movie of the black hole with the help of space telescope, and also new generation event horizon telescope, and that will be very useful to us. Further, there can be many, because at the moment we are able to solve around 20 angular position of the 20 micro arc second. In the future it can be further increased, right? By adding the telescope we can increase. Now what we are doing, we are using earth side telescope. This is the topic of the another lecture that I will not do, and I will stop you on the time. Thank you so much, and it is open for question.
Thank you so much, Professor Ghosh, for this wonderful talk. Participants have few questions.
Can I answer Salman Khan's question?
Yes, sir.
Okay. His question is, there is any studied where lensing has been studied using quantum dynamics? Is that this is the question? I want to tell you that sim it has the quantum gravity doesn't have its own field equation and all. So it can be done only classically, right? But in the solution, I consider rotating Simpson Richter black hole, but we can consider quantum corrected black hole, which we have done. My student Misbah has done, and we have published the paper in Astrophysical Journal, where we have looked into the quantum effects, and also I have seen this effect using uh, by Safkat and Jitendra. These two students have studied the effect of the gravity effect. So we have studied quantum motivated black holes and studied it lensing, this thing, all these things. You can see in the paper. If you, I can send you the details. Yes.
Any other one? Uh, okay. I forget one. There are so many achievements to his credit. I mean, to Professor Ghosh. But let me mention recent one. So let me congratulate to Professor Sushant Ghosh for the formulation of Ghosh-Kumar rotating black hole. It is the great achievement for Professor Ghosh and his student. Many scientists around the world are working on Ghosh-Kumar black hole.
Also
So,
Ghosh black hole. Are
yes, yes,
Shyam
sir.
only, there is only Ghosh black hole also.
Okay, sir. Okay. So let me invite Professor Shamun Ahmed Siddiqui, Head Department of Physics, Integral University Lucknow, uh, to deliver the vote of thanks.
Thank you, Dr. Shah Alam. So, first of all, am I audible?
Yes,
Yes,
yes.
sir.
Yeah. So, first of all, I would like to extend my gratitude to the top leadership of Integral University, that includes Honorable Chancellor, Honorable Pro Chancellor, and Honorable Vice Chancellor, that they are continuously encouraging us to organize such type of programs. I'm also very much thankful to the Dean Faculty of Science, Director, Human Resource Development Center for their continuous support. And I am very much grateful to Professor Ghosh that he delivered his lecture on such an interesting topic of astrophysics, and he explains the complex and very intricate phenomena of astrophysics in very simple and elegant way, such as the Kerr black hole, non-Kerr black hole, and how non-Kerr black hole reduces to Kerr black hole, and the gravitational lensing by rotating Simpson-Wizard black hole, etc. So earlier we scheduled this lecture in physical mode, but since we are approaching the end semester examination, so we scheduled this lecture online. And for sure, next time we will certainly request Professor Ghosh to visit Integral University so that our faculty members, research scholars, and students may get maximum benefit from his knowledge and vast experience. So, thank you very much, sir, for such
Thank
a
you. Thank you,
nice
sir.
talk.
Thank you.
Okay, sir. We can leave now.
Okay. हो गया
हाँ हाँ